Hey class, these are the notes for homework number 15, part 1. Part 2 will get posted a little bit later, probably tomorrow. I'm covering piecewise functions. There's also videos from Grant already posted for trig stuff and piecewise functions, so you can look there as well. This is degrees, radians, and trigonometric functions, the trig part of this homework. And this is where we're definitely getting into trigonometry now for the next rest of the quarter. Let's start at the beginning. So there's this idea that one full revolution of a circle has an angle of 360 degrees. Kind of an arbitrary choice. It was probably picked because it was close to the number of days in the year, also because it's divisible by a lot of different numbers, right? 360 is divisible by 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, 20, 18, lots of numbers. Anyway, so the angle for a circle is 360 degrees. The circumference of a circle with radius r is 2 times pi times r. So for example, if your radius was 3 inches, your circumference would be 2 pi times 3 inches, which is 6 pi inches. And if you put that into a calculator, 6 times pi is approximately 18.8 inches. So you can't quite see that. The glare is terrible there. 18.8 inches. But we don't really care. So it's 6 pi inches. We do want to leave things in terms of pi. Typically, we don't usually want to approximate pi. This leads us to the idea that the angle of one full revolution of a circle is 2 pi radiuses long, or 2 pi radians. Literally, the angle needed to go a length of 2 pi radii around the circle. I'll talk more about this in just 1 second. But I just want to point out that we're going to use this equivalence here, that 360 degrees is equal to 2 pi radians. They're both measures of angles, degrees versus radians. And if we divide both sides by 2, 180 degrees is equal to pi radians. Let's talk a little bit more about that. Now, I will point out, the next page you could probably just skip over. You don't really need to know exactly where this comes from to be able to do the computations. That said, I still think it's worth watching. So, also point out, there's a really good short video I posted on Canvas about how a radian is defined. I highly recommend you watching it because the animation I think is super useful. But I'm also going to talk about it here. So, in a circle of radius 1, which is a unit circle, and really you could use a circle of any radius, but it's convenient to use a circle of radius 1. The angle theta subtending an arc length of 1. So what does that mean, subtending an arc length of 1? It means that if on this circle, you took a length around the circle that was just 1 long, so if that's a length of 1 there, that's your radius equal to 1, then the length of 1 here is probably about there. So maybe like from there to there also is 1 long. So that arc length, which we often use the letter S for, is equal to 1, which is the same length as the radius. So that arc length there is really 1 radius worth of length. And if the arc length is 1 radius long, then the angle subtended by the arc, meaning the angle that if you measure essentially from the circle from there to there, that angle, which we usually call theta, spelled Theta if you care. So theta is spelled as Theta. This angle is said to be 1 radian because the arc length it goes along with is 1 radius long. That's it. That's the whole definition of a radian, is that the angle measure in radians is just how many radii it would take to get that angle. So very importantly, I'll point out that half a circle, the circumference, or I should say the arc length of half a circle, is pi times the radius, just like the circumference was 2 pi times the radius. So this length, in fact, I'm going to label it here. So this length in red, if I went actually on the circle, that length would be pi. Because again, the circle has a radius of 1. The circumference would be 2 times pi times the radius, which is just 2 times pi, which is approximately 6.28. This length here is half of that. It's half of the circumference, which is just pi. What that means for us is that if the arc length is pi, then the angle corresponding to that arc, which is half a revolution, that angle there is an angle of pi. So half a revolution, the angle, which I'll give a different name to since I've already used theta here. Let's call this angle alpha. We usually use Greek letters. The angle alpha there is equal to pi. So going halfway around the circle means our angle is pi radians. Now we don't usually write the radians, we just leave that off. But the angle there is pi radians. So, and again, if you went all the way around the circle, well, the arc length would be 2 pi, literally a measure of 6.28 approximately. And the angle would also be 2 pi radians. So the arc length and or I should say the arc length as a measure of how many radiuses it takes to go that far. And the angle in radians are exactly a 1-to-1 correspondence. We'll do one more here. So I'll point out that this arc length here is a quarter of the circle long, or quarter of the arc length, or quarter of the circumference. So from here to here, that arc length, which I'll use S for, is the total circumference, 2 pi divided by 4. 2 pi divided by 4 equals pi over 2. Pi over 2 radii, because the radius is the length of 1. So this is the length of pi over 2 times the radius. But that exactly means that this angle here, which I'll call beta, beta is exactly equal to pi over 2 radians. Or in degrees, it would be 90 degrees. So there's always this correspondence between an angle in degrees and an angle in radians. And the way we convert from one to the other is by using the fact that pi radians is equal to 180 degrees. So if that didn't make 100% complete sense, that's okay. You can still do the computations without understanding all that, but I really, really, really would encourage you to try to understand it and to definitely try to watch that short little video about the meaning of a radian, because I think it helps you understand, oh, we're just talking about how many radii worth you would need to get that angle. So 1 radius of length here corresponds to 1 radian of angle there, which is approximately like 57 degrees. So I will point out that 1 radian is approximately 57 degrees. And so I'll point out that 6 radians is approximately 6 times 57 degrees, which is 342 degrees. And that's almost a full revolution. But a full revolution isn't 6 radians. A full revolution is 2 pi radians. And 2 pi radians is exactly, well, 2 pi times approximately 57. And it won't be exact, but I will point out that if we do the math here, 2 times pi, there's the pi button here. It's always a mystery. 2 times pi times 57. Oh my gosh, let's convert that to, is about 360. Well, not perfect, because again, I'm approximating 57 degrees there, but it seems reasonable that, oh yeah, a full revolution is exactly 2 pi radians worth of radians. Okay, on to the math. So converting between degrees and radians is pretty straightforward. Let's talk about a different conversion though first. To convert 3 feet to inches, we would multiply by 12 inches per 1 foot. Always the unit that you want to end up with in the numerator, the unit that you're trying to cancel in the denominator. And then we take 3 feet, multiply it by 12 inches per 1 foot. And the feet would cancel, and you end up with 3 times 12, which is 36 inches, which makes sense, right? We know that 3 feet is 36 inches long. In the same way, to convert from feet to inches, we multiply by 1 essentially, right? Because 12 inches divided by 1 foot is equal to 1. They're the same number, just written in different units. To convert from degrees to radians, we would multiply by 180 degrees divided by pi radians, also known as 1, right? That is also equal to 1. It's just kind of weird. Units are important. Similarly, to convert from radians to degrees, we multiply by the reciprocal. Pi radians divided by 180 degrees. So if you're trying to get degrees, you want degrees on top. If you're trying to get radians, you want radians on top. And again, we don't write RAD or radians or rad. We just know that if there isn't a degree, it means radians. If there is a degree, it means radians. By degree, I mean the little circle symbol there. So let's convert 60 degrees to radians. So we're going to take our 60 degrees. We're going to multiply it by pi over 180. If it helps, although you don't have to do this, you can think that's 60 over 1. So if this is 60 over 1, although I don't think you need to write that, then we can multiply this as 60 pi divided by 1 times 180 is 180. The degrees canceled. And I'm going to reduce this fraction. And we should always reduce these fractions. So you get 6 pi over 18. And then 6 and 18 both have a factor of 6. So we're going to reduce this to pi over 3. And that would be the same angle measured in radians instead of in degrees. So 60 degrees is equal to pi over 3 radians. They have the same measure. They both look like about like that. That angle there is 60 degrees or pi over 3 radians. Cool. So let's do some more conversions. So we're going to convert the following angles from degrees to radians, and we're going to simplify the fractions as much as possible. So the first step is always just to multiply our angle in degrees by pi divided by 180. I don't think you need to write 45 over 1, but you can. But what's going to happen here is you're going to get 45 times pi over 180. Degrees canceled. Now it's a measure in radians. And then we're going to reduce that fraction. So 45 and 180 are both divisible by 9. 45 is 9 times 5. 180 is 9 times 20. And cancel the 9s. I'm showing more work than I really need to here. And then 5 and 20 both have factors of 5. So that reduces. Oh, sorry. There shouldn't be a pi there, though. Excuse me. That should be 5 pi over 20. And then we can reduce that to pi over 4. Cool. Let's keep going. So this is the general idea. To convert from degrees to radians, you multiply by pi over 180, and you reduce the fraction. So 120 degrees is equal to 120 times pi radians over 180 degrees. That's going to be 120 pi over 180. When they both end in 0, it's really easy to reduce that. You can reduce this to 12 pi over 18. 12 and 18 both have a factor of 6, so we can reduce this to 2 pi over 3. 12 divided by 6 is 2. 18 divided by 6 is 3. A negative doesn't really affect anything. We just have a negative in the end. So I'll point out that when you're drawing an angle, you usually draw it like I was doing over here, starting at the positive x-axis and going in a counterclockwise direction. If the angle is negative, we go in a clockwise direction instead. So which kind of seems kind of backwards, right? It's anti-clockwise, but anti-clockwise is the positive angle. Regular clockwise is a negative angle. I don't usually say anti, I say counterclockwise, but people say anti-clockwise as well. So negative 150, negative 150 degrees is going to be negative 150 degrees times pi over 180. That's going to be negative 150 times pi over 180, which reduces to negative 15 pi over 18, which reduces to negative 5 pi over 6. Keep going. 310 degrees times pi over 180 degrees. So I can see that when they both end in 0, it's going to simplify to not have them in 0. So I'm going to rewrite this as 31 pi over 18. And I think that's as simple as it gets because 31 is a prime number, so it doesn't have any factors in common with 18. Same deal here. 50 degrees is equal to 50 degrees times pi over 180. And again, we can simplify that straight to 5 pi over 18. And it can't be reduced any further. 9 degrees is 9 degrees times pi over 180 degrees, which is going to be 9 pi over 180, which reduces to pi over 20. Cool. Let's go the other direction. Convert the following from radians to degrees. So now if we want to start with radians and end degrees, we're gonna have to multiply by the conversion factor with the degrees on top and the radians on the bottom. So we're going to say that 3 pi over 4 is equal to 3 pi over 4 times 180 divided by pi. 180 degrees divided by pi. So two important things happen here. First, the pi's cancel. And now I have 3 times 180 degrees divided by 4. And here's what I would recommend. You can either do the multiplication first or the division. So you could do 3 times 180, which is 540, and then divide that by 4, which is going to be, I don't know, something. Or you can do the division first, but I usually find it to be easier. So I can reduce this to 3 times 90 degrees over 2, right? Because 90, 180, sorry, 180 and 4 both have factors of 2, so I cancel the 2 essentially from each of them. And then it actually might make sense to do the multiplication here first. 3 times 90 is 270 degrees. 270 degrees divided by 2 is 135 degrees. There are definitely other ways to get there. I'm just trying to do the least amount of mental math I can make happen. Same deal here. Pi over 6, we're going to multiply by 180 degrees over pi. When you're changing a measure, an angle measure in radians to degrees, and your original angle has a pi in it, which most of them will, but they don't have to have. If it has a pi, then when you multiply by 180 degrees divided by pi, the first thing that's going to happen is the pi will cancel. So we're going to get 180 degrees divided by 6. And 180 divided by 6 is 30, because 18 divided by 6 is 3. So you get 30 degrees. We do need to write the degree symbol to make sure that we know it's a degree. Whereas in this all of these other ones here on this previous page, none of these have the degree symbol because they were all measures of radians. Okay. Same deal over here. We're going to multiply pi over 2 by 180 degrees over pi. The pi's cancel. And we get 180 degrees divided by 2, which is 90 degrees. Same deal over here. It's doing the same thing. 4 pi over 9 times 180 degrees over pi. It is good to show your work for these. Pi's cancel. You get 4 times 180 degrees over 9. And this is a great example of where doing the division first is the better call. 4 times 180 is 720. 720 divided by 9 is 80. But it's much easier to say that 180 divided by 9 is 20. Then you have 4 times 20 degrees, which is 80 degrees. I think it's much easier that way. 8 pi is going to be 8 times. So so it wouldn't be wrong to say it's 8 times 180, but I should probably show my work. So I should say it's 8 times pi times 180 degrees divided by pi. And then the pi's cancel, and you get 8 times 180 degrees, which I don't know off the top of my head. I would do it as times 2 times 2 times 2 personally. So 180 times 2 is 360, times 2 is 720, times 2 is 1,440. 1,440 degrees, which is essentially 4 full revolutions, which makes sense because 8 pi is really 4 times 2 pi. And we know that 2 pi radians is 1 full revolution. So 4 times 2 pi, which is 8 pi, should be 4 full revolutions. Which is kind of weird to think about more than 360 degrees, but it's totally something we do. Okay, this last one's a little bit tricky. It doesn't say 9 pi. It doesn't say 9 degrees. It just says 9. We should definitely see this. If there isn't a degree symbol there, this is 9 radians. So we're going to multiply this to change it to degrees by pi over 180 degrees. Sorry, I messed that up, right? Not times pi over 180. But see, it's confusing, right? Because it looks like it's in degrees and I'm trying to get it to radians, but that's not the case. It's in radians and I'm trying to change it to degrees. So I'm going to have to multiply by 180 divided by pi. And this answer is going to be a little bit unsatisfying. 9 times 180 is what? 900 plus 720 is 1,620 over pi degrees. And that's our exact answer. And without the calculator, and really even with the calculator, we shouldn't change this to a decimal approximation. I will tell you that using a calculator, the decimal approximation is, let's see, 1,620 divided by pi is approximately 515.7 degrees. This is still the answer I want. and it does have to be in degrees. 9 radians does make sense. It should be more than a full revolution because we saw that a little more than 6 radians was one full revolution. So 9 radians is like 1.5 revolutions, which is like 540 degrees. So yeah, that seems about right. So that's the whole idea of converting between radians and degrees and radians. The other thing we have to talk about, which is super important, is the definition of the 6 trigonometric functions. So the 6 trigonometric functions, or the 6 trig functions, as we will often abbreviate it, given an angle theta, right there, it has to be one of the acute angles, can't be the right angle. Given an angle theta in a right triangle, we define the 6 trig functions as follows. So typically, for an acute angle theta, acute just means less than 90 degrees, bigger than 0 degrees. In a right angle, we define or label the 3 sides as follows. So this longest side that's always opposite the 90-degree angle is always the hypotenuse. And then the side that the angle isn't in between, so the side angle is in between this side and this side, the other side over here is called the opposite side. This is opposite of the angle. And then this side that's next to the angle that isn't the hypotenuse is called the adjacent side. So then we define 6 trigonometric functions to be 6 ratios. Sine of theta is defined to be the opposite over the hypotenuse. Cosine of theta is defined to be the adjacent over the hypotenuse. Tangent of theta is defined to be the opposite divided by the adjacent. Those are like your primary trig functions, sine, cosine, and tangent. And then you have your reciprocal trig functions. So cosecant of theta is the reciprocal of sine theta. It's defined to be the reciprocal, the hypotenuse divided by the opposite. Secant of theta is the reciprocal of cosine theta. Secant of theta is defined to be the hypotenuse divided by the adjacent. And finally, cotangent of theta is the reciprocal of tangent of theta. It's defined to be the adjacent divided by the opposite. You definitely should memorize these. Specifically, you should memorize these 3, which there is a mnemonic device people use. It's called ka. You have to emphasize the A sound there. Toa. Ka, toa. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And then these 3 are the reciprocals of the ones they're next to. So cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. Cotangent is the reciprocal of tangent. The way I kind of remember it is each reciprocal pair has one regular and one co-function. So we have sine and cosecant, cosine and secant, tangent and cotangent. That's one way that kind of helps me remember which, basically, I know that tangent and cotangent go together, and then I know that sine can't go with secant because one of them has to be a co. So sine has to go with cosecant as a reciprocal, and cosine has to go with secant as a reciprocal. All right, so definitely want to memorize those. So katoa, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. And then we're going to use these definitions to evaluate the 6 trigonometric functions of some triangles. So find the 6 trig functions of the angle theta in the right triangle below. So first I'll point out which side is the adjacent and which side is the opposite depends on which angle you pick. So since this is the angle, the 8 is the length of the opposite side, and the 6 is the length of the adjacent side. And the length of the hypotenuse hasn't been given to us. So we have to find it. How do we find the length of the third side? We use the Pythagorean theorem, which says the following. In a right triangle, which we often label the sides as A, B, and C, where C is the length of the hypotenuse and A and B are the lengths of the legs, it is true that A squared plus B squared equals C squared. If I want to find the length of my hypotenuse side here, which I could label as C, or really anything you want, it's going to be true that 6 squared plus 8 squared is equal to C squared. 6 squared is 36, 8 squared is 64, C squared is C squared. 36 plus 64 is 100. So then C is equal to, I don't want to say plus or minus here, although normally I would have C squared is equal to 100. The two solutions would be C equal to positive 10 and C equal to negative 10. But since C is representing a length of a side, it should be a positive number. So C is going to equal just the square root of 100, which is going to be 10. So that's my hypotenuse. Sometimes, like in the next example, you won't be able to have a nice number as your length. Like you might just get the square root of something and have to leave it as the square root of something. All right, so let's find sine, tangent, cosine, sine, cosine, tangent, and all the rest of this angle. So sine of theta is going to be the opposite divided by the hypotenuse, which is going to be 8 over 10. And I really should reduce that to 4 over 5. Cosine of theta is going to be the adjacent over the hypotenuse, which is going to be 6 over 10. And I should reduce that to 3 over 5. And tangent of theta is going to be the opposite over the adjacent, which is going to be 8 over 6, which reduces to 4 over 3. And then the nice thing about the reciprocals is you actually can just, if you write it in this way, you don't have to really think about it. You can just say, well, it's going to be all these fractions flipped over. Or we can do the math. I'll point out that cosecant, I know it's cosecant of theta is going to be 5 over 4. But let's do the math. Cosecant of theta is the hypotenuse over the opposite, which is 10 over 8, which reduces to 5 over 4. Secant of theta is the hypotenuse over the adjacent, which is 10 over 6, which reduces to 5 over 3. And cotangent of theta is the adjacent over the opposite, which is 6 over 8, which reduces to 3 over 4. We should reduce our fractions if we can. And I will point out again that if you find sine of theta, cosine of theta, and tangent of theta, you don't have to really do any work to find cosecant, secant, and cotangent. You just have to take each of the sines, cosines, and tangent values and find the reciprocal of them. So I could have just said, oh yeah, cosecant of theta is 5 over 4, secant is 5 over 3, cotangent is 3 over 4. I will also point out, not required, but I'm kind of a stickler when it comes to how you say these. So you shouldn't say sin or cos or tan. You should say sine, cosine, and tangent. I'll just point out, I'm going to write them down. Sine, cosine, tangent. You don't write these out when you write the functions. You write them like this. But really, these are the things you should be saying. Sine, cosine, tangent, cosecant, secant, and cotangent. So make me happy, say them the good way, not the wrong way. It is kind of wrong. So anyway, please do say them correctly. It sounds much nicer. All right, let's do another one. Find the 6th trig function of the angle alpha in the triangle below. Please rationalize any and all denominators. That means if we end up with a radical in the denominator, we have to do some work to get it out of the denominator. So I'll point out that we're missing the side again. So before we were missing the hypotenuse, now we're missing one of the legs. So I'm going to call this side, I don't really care what you call it. You call it A, B, C, F, X, whatever. Let's call it B though. So we're going to say that 4 squared plus B squared equals the square root of 41 squared. 4 squared plus B squared equals the square root of 41 squared. So then 16 plus B squared equals 41. B squared equals 41 minus 16, which we have to subtract. 41 minus 16 is 25. So B squared equals 25. So B is equal to the square root of 25, which is 5. B is equal to 5. I'll also point out, as far as alpha is concerned, this side is the opposite. This side is the adjacent. And this longest side, which is always opposite the 90-degree angle, is our hypotenuse. All right, let's find all the things. So sine of alpha is the opposite over the hypotenuse, which is 5 over the square root of 41. We're going to have to rationalize that because we have a radical in the denominator. So we multiply that by the square root of 41 over the square root of 41. And we end up getting, in the numerator, 5 times the square root of 41 and 41 in the denominator. And if 5 over 41 can be reduced, I would reduce it, but I can't. So we leave it as is. Same thing for cosine of alpha. Cosine of alpha is going to be the adjacent over the hypotenuse. So 4 divided by the square root of 41. And again, we're going to rationalize by multiplying by root 41 over root 41, which is going to be 4 times the square root of 41 over 41. Tangent of alpha is the opposite over the adjacent. which is going to be 5/4. That's all, that doesn't have an irrational denominator, so we'll leave it as it is. I would leave it as 5/4. You could write it as 1.25 if you prefer decimals, but I don't encourage that. Now, for the rest of these, let's be super smart about this. I don't want to take the reciprocal of this because that's going to end up with a radical on my denominator. I should take the reciprocal of 5/√41 and get √41/5. Or I could literally just look at the triangle and say, oh yeah, it's going to be the hypotenuse over the opposite, which is √41/5. Similarly, secant of alpha is the hypotenuse over the adjacent, √41/4. Or again, it's the reciprocal of this before I did the rationalizing. It's √41/4. And finally, cotangent of alpha should be the reciprocal of tangent of alpha, which should be 4/5. Or adjacent over opposite. So once you know these three, you can find these three just by finding the reciprocals. Also, I should give you a code for the early access to the homework if you want it. So the code, which I'm going to make up right now, is going to be Trig 15 for the homework number 15. There you go. There's your access code for the homework if you want to start it early. Cool. Got a couple more things to do, and then we're done with this. I kind of feel like I should do one more example. Yeah, let's do one more example real quick. More papers right here. So let's say we were given the following triangle. Let's say we had, I'm gonna make up some numbers here. Let's say we have this triangle where we know that this side was 5, this side was, sure, let's say this side is 7, and we want to find, we don't know this side here. And this is the angle that we're dealing with. Let's call it theta. We want to find the 6 trig functions of theta. We first have to find this angle, sorry, this side. So we're going to say 5 squared plus whatever that question mark is squared equals 7 squared. So the question mark squared equals 7 squared minus 5 squared. Be careful, you can't just take the square root of each thing and say it's 2, right? We can't say that the question mark is 7 minus 5. The question mark, actually, let's simplify this. So the question mark squared is 49 minus 25, which is 24. So the question mark itself is equal to the square root of 24. And although you could simplify this as 2√6, I wouldn't recommend it. I would just leave it as the square root of 24. We do not need to simplify our square roots. So then sine of theta is going to be the opposite over the hypotenuse, which is the square root of 24/7. Cosine of theta is going to be the adjacent over the hypotenuse, which is 5/7. And tangent of theta is going to be the opposite over the adjacent, which is the square root of 24/5. If it helps, I do recommend labeling these, right? As far as theta, well, this side, and I didn't label my right angle, sorry, but it should have been hopefully clear. This is definitely your hypotenuse. This is definitely your adjacent side because theta is right there. And this is definitely your opposite side because of opposite theta. So, and then we can find the rest of them. Cosecant of theta is the reciprocal of this, which is 7/√24. I'll come back to rationalize in a second. Secant of theta is 7/5, the reciprocal of that. And cotangent of theta is the reciprocal of tangent, which is 5/√24. And then for these two that have a radical in the denominator, we'll multiply by √24/√24. I end up getting 7√24/24 and 5√24/24. There you go. So finding the 6 trig functions of a particular angle in the right triangle is usually not too hard. Definitely have to remember though that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, cosecant is hypotenuse over opposite, secant is hypotenuse over adjacent, cotangent is adjacent over opposite. And then make sure that when you look at the triangle, you look at where your angle is, you'll be like, okay, the long side opposite the right angle is the hypotenuse. The other side next to it is the adjacent, and the side that's not in between one of the two sides, that's the opposite side. All right. Last thing, using a calculator to estimate trig functions of angles. So when you're using a calculator to estimate trig functions of angles, you have to make sure that you're in the right mode, degrees or radians. If you see a degree symbol on the question, you have to use degrees. If you don't, you have to use radians, even if it looks like it should be a degree. So for example, if I want to find sine of 80 degrees, I have to make sure the mode I'm in is degrees, which I'm in degrees. So I'm going to quit, and then I'm going to do sine of 80 degrees and get approximately 0.98. And I would say 2 decimal places unless otherwise asked for. On the other hand, if I change my mode to radians and then quit and then do sine of 80 now, it's going to be a wildly different answer. Negative 0.99. I don't know why I put the 0 here, not there. So it's a very different angle, so you're getting a very different value. A couple more examples just to make sure everyone's here. So if I wanted to find, say, cosine of 25 degrees, again, I would make sure I was in the degree mode. I have to switch back. And then I do cosine of 25, which is approximately 0.9091. I guess just a round up. If I wanted to find secant of 25 degrees, I will point out that my calculator does not have a secant button. So I have to find the reciprocal of cosine. Secant of 25 degrees is going to equal 1 divided by cosine of 25 degrees. So I'm going to do 1 divided by cosine of 25 degrees. And that's going to be approximately 1.1. In a similar way, if I wanted to find cosecant of, say, I don't know, pi over 3, well, that's definitely in radians because there isn't a degree symbol there. So I'm going to first say, well, I know that's going to be 1 divided by sine of pi over 3, or the reciprocal of sine of pi over 3. So I'm going to change my mode to radians. And then I'm going to do 1 divided by sine of pi divided by 3. And okay, so some calculators are smarter than others. My calculator knows that that's a special angle. It's a very well-known value for 1 divided by sine of pi over 3. But I want a decimal approximation here. So even if it gives me something nice like that, I'm going to hit this button to get the decimal approximation, which is approximately 1.15. So again, be careful, right? If something annoyingly says sine of 80, even if it looks like it should be a degree, if it doesn't have the degree symbol, you have to assume it's in radians. Let's do 2 more. Let's do tangent of 2 degrees versus tangent of 2 radians. So I'm in radians right now, so let's do tangent of 2 radians first. So tangent of 2 radians is going to be approximately negative 2.2, whereas if I change my mode to degrees, tangent of, sorry, I can't quite see that. Tangent of 2 degrees is now going to be about 0.03. Again, very different. So make sure you're in the right mode. You have to be in degree mode if you see the degree symbol. You have to be in radian mode if you don't see the degree symbol, whether it looks like it should be in degrees or not, right? That's tangent of 2 radians. That's cosecant of pi over 3 radians. That's sine of 80 radians. Kind of stupid, but if you don't see a degree symbol, you have to assume it's radians. And I think that's the last page. Let me double check. Yep, that's it. So there is converting degrees to radians, radians to degrees, and evaluating the 6 trigonometric functions of angles in right triangles. Hope that was good.